Alrighty. Today we're drinking some espresso coffee on this Monday, and we got a fresh new paper for you guys here. This is Magic3D, high resolution text to 3D content creation coming out of NVIDIA. So these guys have a great little landing page here, so we're going to kind of look at some pretty pictures and get motivated before we go to the actual paper. So this is another kind of, I love these sliders. Look at that. You can look at the, this is the normal, right? So that roughly shows you what part of the mesh is pointing up and down based on the red to green color. But then you can actually go over it and see the color of the actual texture. So Magic3D can create high quality 3D textured mesh models from input text prompts. It utilizes a coarse-defined strategy that leverages both low and high resolution diffusion priors, right? So you have low and high resolution, so you have kind of this pyramid type design, which is pretty common in a bunch of other computer vision where you have different resolution models. Magic3D synthesizes 3D content with 8 times higher resolution than Diffusion while also being 2 times faster. So Diffusion, we also went over that paper on this channel. Feel free to go back and look at that if you want, but I feel like this one's going to be the superset version of that. Look at that, peacock riding a surfboard, a bagel, Leaning Tower of Pisa. That's quite impressive, right? So little artifacts here, like for example, the Sydney Opera House. You see kind of underneath this model, there's kind of this weird amorphous blob. So I wonder if they do any post-processing to kind of close these meshes from the photogrammetry world, right, where people use a bunch of images to get a 3D model of a object. There's all this kind of post-processing stuff that happens afterwards where you kind of simplify the mesh and close holes in the mesh and smooth out certain areas of the mesh. So I wonder if they're using those types of tools or whether this is literally how they come out. Prompt-based editing. We can also condition the diffusion model on an input style to transfer its style to the output of the 3D model. That is crazy. I wonder what the 3D meshes for these look like. Okay, and then what is the method? We utilize a 2-stage coarse-defined optimization framework for fast and high-quality text to 3D. So there's kind of a 2-part process here. In the first stage, we obtain a coarse model using a low-resolution diffusion prior and accelerate this with a hashed grid and sparse acceleration structure. Okay, so there's a 3D mesh extraction, which they call DMTET. Then once you have this simple 3D mesh, then you're using this. Oh, okay, so there's here diffusion on the image, and I guess here diffusion in the latent space. And then high resolution optimization versus low resolution optimization. Okay, I'm sure we'll learn more once we go to the paper, but I wanted to kind of start on this just to motivate it and show the cool pictures. Cool, so let's go ahead and open this paper in good old paper pile. Let's get our highlighter ready and let's get started. Let me take a sip of this and then we'll get started. All right, so again, we have kind of relatively large team here. Right, these asterisks usually indicate that these people all did the same amount of work, right? So down here, equal contribution. So this is a 1, 2, 3, 4, 5-person project. Pretty significant. Usually, the more people, usually the more impressive. Although that's not always true. 18th of November. So literally just less than a week ago. And NVIDIA. NVIDIA is kind of the best, I would say, when it comes to Nerfs in 3D. Okay. Diffusion has recently demonstrated the utility of a pre-trained text-to-image diffusion model to optimize neural radiance fields. Okay. Achieving remarkable text-to-3D synthesis results. Okay, that's kind of cool that they start with a reference to Diffusion directly in the abstract. You don't really ever see references in the abstract, so I think it's commendable that they do that. And also the fact that Diffusion is a competitor, right? It's out of Google, so the method has two inherent limitations: extremely slow optimization of Nerf, and B, low resolution image space supervision on Nerf, leading to low quality 3D models with a long processing time. Okay, so basically the main things that they hit on Diffusion for is that it's slow and it's not that great. We address the limitations by utilizing a two-stage optimization framework. Okay. Why is this text so hard to highlight today? So you have a two-stage pipeline. First, we obtain a coarse model using a low-resolution diffusion prior and accelerate with a sparse 3D hash grid structure. Okay. We're going to have to learn what this is, this sparse 3D hash grid structure. We further optimize a textured 3D mesh model with an efficient differentiable renderer interacting with a high-resolution latent diffusion model. Our method, dubbed Magic3D, can create high-quality 3D mesh models in 40 minutes, while also achieving high resolution. Together with the image condition generation capabilities, we provide users with a new way to control 3D synthesis. Awesome. I really hope they release this, right? 3D digital content is important. And it's getting everywhere, right? The metaverse is taking over. Yeah. I think this is the important part. Much like how stable diffusion, and there's some controversy about it, that it's extremely hard to learn how to do art, and there's people who spend decades perfecting that craft, and 3D content creation is the same. Modeling and making the textures for 3D assets takes decades to learn to do very, very well. So giving that capability to anyone who can type a description is a huge democratization step. Yeah, so one thing they say is that there's not a lot of 3D datasets on the internet. I would actually say that this isn't true. There's a couple different websites such as Sketchfab, for example, that have huge amounts of 3D models, right? You just have to kind of know where you're looking. And I think unlike image data sets, which you can probably collect and use without infringing on any copyright, I think the problem is that these 3D data sets are all owned, and each individual model is owned by someone, and they have different licenses, so it's very difficult to maybe create a data set without stepping on someone's toes. Text condition 3D by utilizing a pre-trained text-to-image diffusion that generates images as a strong image prior. So this is Dream Fusion. This is how Dream Fusion works. The diffusion model acts as a critic to optimize the underlying 3D representation. The optimization process ensures that it rendered images from a 3D model represented by a neural radiance field match the distribution of photorealistic images across different viewpoints given the input text prompt. Yeah, I think they like explicitly actually use ways of describing these viewpoints in the text, right? So they might say a frog with a crown from the top, a frog with a crown from the side, and then they're trying to get the Nerf to match that. Stream Fusion cannot synthesize high-frequency 3D and geometric texture details. So what does high frequency mean in this case? So frequency, right, describes the how many times a wave goes up and down, right? If you think of like a little sine and cosine wave, how many times it goes up and down within some unit time. But now you're asking, okay, well, how does that apply to geometric and texture details? So whenever people say low frequency details and high frequency details, what they're really meaning is kind of the scale. So low frequency actually means large scale, right? Like, I don't know, maybe the finger and the hand and then the wrist, that would be low frequency. High frequency details would be the actual like texture of the finger, right? And these like tiny little lines. So the smaller and finer details. The reason they say high frequency is because there's this trick in math where you can decompose any function into its frequency makeup. So you can say this curve here is made up of this low frequency sine or cosine added to this other set of high frequency sine and cosines. So that's kind of where that word comes from, but sometimes I feel like it's overly complicated. You should just say high or fine detail or small details. Okay, so here they say that even at their low resolution of 64 by 64, generating one model takes 1.5 hours. Silver platter piled high with fruits. Okay, this is just examples. Beautiful dress made out of garbage bags. That's quite impressive. The reflection on that is what's impressive to me. Which makes me think that the textures that they're putting on these objects aren't just color. They also have textures, or things like emissivity and metallicness, roughness. So different float values that go along with each color, right? So rather than each little dot here being represented by RGB values, you have additional values that represent kind of how light bounces off of it, how rough that material is, and that allows you to render it nicely. Quality. Okay, high resolution text to 3D. Okay, it's the top. Bottom, high resolution prompt based editing. Magic3D can edit 3D models by fine tuning the diffusion prior using a different prompt. Taking the low resolution 3D model as an input. Okay, I wonder if this is a real 3D model or if this is also generated. Magic3D can modify different parts corresponding to the different input text. Magic3D is a convenient tool for augmenting 3D content creation. In the first stage, we optimize a coarse neural field representation akin to Diffusion, but with a memory and compute efficient scene representation based on a hash grid. I think they actually, yeah, I kind of recall this. I feel like we actually looked at this paper. Yep, we did look at this paper. Instant neural graph primitives with a multi-resolution hash encoding. I do remember this. So, instant NGP, I think it was called, or something like that. But basically, they used a different way of encoding the scene, such that you got a significant speed up in the creation and rendering of Nerfs. So that basically seems like it's the meat of this paper. All they basically did is take Diffusion, but then put their special sauce where you can get the memory and compute efficient version on there. In the second stage, we switch to optimizing mesh representations, a critical step that allows us to utilize diffusion priors at resolutions as high as 512 by 512. Okay, so diffusion priors just kind of means that they're going from an image, and then in Diffusion, that image is 64 by 64, right? That prior that they're conditioning their generation on. But here, the prior image that they're conditioning their generation on is 512 by 512. 3D meshes are amenable to fax graphics renders that can render high-resolution images in real time. We can leverage an efficient differentiable rasterizer and make use of camera close-ups to recover high-frequency details in geometry and texture. Okay, that's interesting. So maybe not only do they look at different views of the 3D object to render the different parts of it, but then they also bring the camera up close, and that allows the model to kind of generate the actual fine details. That's an interesting extension there. It seems like a really simple idea. It's interesting that Diffusion didn't do that, right? Where not only are you saying we can generate a 3D model or a 3D object from 2D objects, or from 2D pictures of that object if we have 2D pictures from all the different views, but we can generate a 3D object that's very high resolution if we also have pictures that are very, very close up of that thing. Our approach produces high fidelity 3D content that can be conveniently be imported and visualized in standard graphics software. Our approach, dubbed Magic3D, endows users with unprecedented control. Okay. 8 times higher resolution and 2 times faster. And then they extend various image editing and do it in 3D. Okay, so, I mean, honestly, like, I'm dying to try this. Do they have actual GitHub for this? Unfortunately, I don't think they do. Magic3D NVIDIA GitHub. .3D game engine called Magic Tech. This is not it. Yeah, they don't actually have it. That's unfortunately. Unfortunate. Little Boo is here to mess things up. Boo is the cat on all the pictures. Okay, text to image generation, related work. They're basically gonna talk about diffusion models here. Diffusion models can compose complex semantic concepts from text descriptions. Cascade of super resolution models. Yeah, so we saw this in some of the other diffusion papers that we were reading, where basically the actual generation is happening at a very small resolution, and then you simply have a kind of super resolution model that takes that small little tiny thumbnail size image and then just makes it into an actual size where you can see things. Yeah, or the step beyond that is that actually you don't even generate it in the final image space, you generate it in a lower resolution latent space, right? .3D generative modeling. So this is all the kind of old approaches that people use with point clouds and meshes. However, volume rendering networks are typically slow to query, leading to a trade-off between training time. Yeah, so they say that a lot of these are limited to modeling objects within a single category, thus lacking scalability. Text-to-3D generation has also gained a surge of interest from the learning community. ClipForge. However, it requires 3D assets in Voxel. Trained. Yeah, I think this is also part of it too, right? Is that they were talking about this too, but like images, it's very easy to convert between the different image types, right? Like on the entire internet, a PNG, a JPEG, like there's a lot more homogeneity between the file formats for these images, and you can convert between them in an automated, simple way, usually. But this is not the case for 3D assets. There's a lot more variety in the types of 3D assets, right? Most of them follow a basic structure where you have a texture, which is the actual like color, and then it wraps around a set of triangular facets that are organized into what's called a mesh. But there's a huge amount of variety in those, and converting from one 3D asset format to another 3D asset format is actually not simple. There is a bunch of tooling that people have built to do that, but even with all that tooling, it's still not an automated process. So getting a good 3D data set is still difficult, just because the 3D file format is much more difficult to deal with. We build upon this work. So I think that's why they keep referencing Dream Fusion here, is because it's largely, they do want to credit the Dream Fusion team with coming up with the main ideas, and all they did here is they just applied the NVIDIA secret sauce rather than Dream Fusion, which was limited to kind of what they had available at Google, and so on. Yeah, they even have a separate background section specifically for Dream Fusion. So there's two key components here. There's the neural scene representation, which we refer to as the scene model, okay? And then a pre-trained text-to-image diffusion-based generative model. Scene model is a parametric function x, g, theta. So x is the image, right? Image x at a desired camera pose. G is a volumetric render of choice, and theta is a coordinate-based MLP representing a 3D volume. Yeah, so I would say this is not quite the right math representation of that, right? Because the image is a function of the camera pose. So really the input is a camera pose. And then that camera pose is fed through a MLP, which is parameterized by theta. And then that produces an embedding, right, or a vector of numbers. And then these numbers are used to render that image in 2D with a volumetric renderer, right? And that usually uses some kind of like ray marching algorithm to render it. The diffusion model, so this is the second part, or the second key component, right, which is just a 2D diffusion model, comes with a learned denoising function, okay, sigma of phi x sub xt conditioned on y and t, where E is the sampled noise. You have x of t is the noisy image. There's a noise level t, right? Because in these diffusion models, right, the way you train them, you're adding noise over. You're basically either removing noise over time or adding noise over time, depending on if you're doing inference or training. So they use t for the noise level because the noise goes up over time or down over time. So at time t equals 0, you have a certain level of noise. At time t equals capital T, you have another level of noise, right? And when you're training, you're adding noise, and then when you're doing inference, you're removing noise or denoising, right? And you're conditioning this denoiser on the text. So you can condition it on anything, but the text, I think, is the most useful, right? Because you can just describe what you want. And it's not the raw text, it's the text that is tokenized and then fed through a, usually not just tokenization, but then also fed through kind of a pre-trained language model until you get a nice little vector. Okay. Provides the gradient direction to update theta such that all rendered images are pushed to the high probability density regions conditioned on the text embeddings under the diffusion prior. Yeah, so your denoiser, your 2D denoiser, is what's kind of ultimately giving you the gradients that you're using to train your multi-layer perceptron that represents the actual 3D object. Okay, Dream Fusion introduces score distillation sampling, SDS, which computes the gradient. Okay, so this is the gradient with respect to the MLP, so the parameters of the MLP, which is theta. This is a loss function, score distillation sampling, loss SDS. The input here, or this is a function of phi, which is the diffusion model, and then g of theta, which is the actual rendering process. And this is the expected value at some time t, right? Or noise level t, if now that we know that the noise is and time are basically the same thing. And you have w of t, which is a weighting function, right? So maybe there's some weights for some views of the objects and a lower weight for other views of the object. It allows you to kind of tune how much each one matters. And here you have the denoised image, right, minus the actual noise, right? So how much is your diffusion model able to denoise the image? Because given that you actually know the noise that you added to the image, right? So you can actually tell how much of that noise it was able to find. Dx d theta. So the derivative of the image x, the final image, with respect to theta. Yeah, so this is kind of how this becomes a gradient, right? If this was just LSDS, then we wouldn't have this dx d theta term. But the fact that they have gradient of theta here, that's why they add the dx d theta here. Okay, we view the scene model, G, and the diffusion model, phi, as modular components of the framework, amenable to choice. In practice, the denoising function is often replaced with another function that uses classifier-free guidance, which allows one to carefully weigh the strength of the text conditioning. Dream Fusion relies on large classifier-free guidance weights to obtain better results with better quality. Yeah. So I think in this sense they're saying classifier-free because a lot of times people will condition this denoising model, right? You could have anything here, right? You could condition this on not just the text embedding Y, but you could also condition it on a class, right? And that's kind of what they were talking about here, where in a lot of these previous 3D generation works, they're conditioning it on the class, such as car or chair or human face. But here, you're not conditioning it on any class, you're conditioning it only on the text. But the text embedding is a much more complicated vector space than the the text embedding is a much more complicated vector field than the actual class embedding, right? If you had a 3D generation pipeline where you were conditioning the diffuser on let's say just one of 12 categories, or even something like Coco, one of 120 or something categories, then right, you're kind of, that's a much simpler space. You're like one of 120 different classes, but the space of all possible text embeddings is so much huger. So conditioning on that, it makes it a lot more difficult of a problem. Okay, so Dream Fusion adopts a variant of MIP Nerf 360. And then image gen as the diffusion model. Okay, high resolution geometry or textures cannot be obtained since the diffusion model only operates at 64 by 64. Yeah. They went from saying high frequency to high resolution. I think some amount of kind of like consistency on that would have been nicer here. Utilizing a large global MLP is both computationally expensive and memory intensive. Yeah, so this is where they're gonna kind of talk about their hash representation. So rather than having one multi-layer perceptron, right, that basically takes the camera pose and a single MLP encodes every single possible view of this image, right? That's what the Nerf is doing. It's basically a neural net that is encoding all of the information of this rabbit. and you can keep making it bigger, and that'll make it more capable of having more information in it. But the hash-based representation will make it more computationally and memory efficient. All right, give me 1 second. I need to go to the bathroom, and then I will return. All right, we're back. Okay, so why don't we actually look high resolution 3D generation. Yeah, maybe, let's not go to figure 2 just yet. I think let's go there once we actually start looking at the different parts of this. But let's continue here with section 4, high resolution 3D generation. So Magic3D is a 2-stage coarse-defined network that uses efficient scene models that enable high-resolution text-to-3D synthesis. We describe our method and key differences from Diffusion in this section. Okay. So there's 2 different diffusion priors in a coarse-defined fashion, right? So they have, this idea goes way back in the computer vision world, right, where you can have different models that deal with different resolutions. So doing things at small resolution, then upscaling, doing things at a high resolution, then downscaling. Actually, the second part would never happen, but first stage, we use a base diffusion model described ediff-I, okay, which is similar to the base diffusion model of ImageGen used in Diffusion. This diffusion prior is used to compute gradients of the scene model via a loss defined on the ray images at a low resolution. Yes, diffusion prior. Okay, it's a latent diffusion model. Right, so what does latent diffusion mean? So here, right, you have a noisy image x of t, and you have noise sigma, and that noise is being added in image space directly. But in a latent diffusion model, you're adding the noise to the latent, not to the actual image itself. And the latent space is usually significantly smaller than the image, right? So let's say you have what they say is a tiny image, right? 64 by 64. That's actually 4,096 numbers, right? Versus like a latent space might be 128 dimensional. So like a order of magnitude smaller. So that's why the latent space is usually more appealing to do the noising and denoising in. Okay, so they say that because they do the diffusion in the latent space, they can basically now use higher resolution images. Yep, is because the diffusion prior acts on the latent Z sub T. The increase in computation comes from computing dx d theta, the gradient of the high resolution rendered image, and dz dx, the gradient of the encoder in LDM. So z is the latent, so the derivative of the latent with respect to the image, and then the derivative of the image with respect to the parameters of the multi-layer perceptron, right? And you can chain rule that. So if you know what the derivative of the latent is with respect to the parameters of the MLP, you can decompose it, and then now you can find the derivative of the image with respect to the parameters of the MLP. Okay, this is the same function as we had before. What is really the difference here? Yeah, okay, so basically this is the same exact function as before, except now we're replacing the image with the, Control Z. We're replacing the image x sub t with the latent z sub t. Cater two different 3D scene representations to the two different diffusion priors at Coarse to find resolutions. Neural fields as coarse scene models. The initial coarse stage of the optimization requires finding the geometry and textures from scratch. Yeah, complex topological changes in the 3D geometry, depth ambiguities from the 2D supervision signals. Right, so when you're looking at a 2D image, it's difficult to know whether there's something that's big that's close to you, or something that's big that's far away, or something that's small and close to you, right? There's this kind of fundamental problem with monocular vision that you can't actually get the actual depth from it. You can kind of infer it based on your priors that you have around the world, right? But you really need multiple images, multiple 2D images to get a good idea of what the 3D structure is. The scene model is a neural field that predicts albedo and density. Okay, that's we're starting to see some of these other things. So it's not just color. You also have albedo, right? Albedo is a way to measure. Sorry if I just gave you a heart attack there. Okay. So yeah, the Nerf, right? This MLP that is predicting the value of every pixel, because you're using this MLP, you're tracing out a ray that comes out from a certain camera view, and then for each point along that ray, you're sampling and you're saying what is the color at that point, right? RGB value. What is the density at that point, right? So you could think of that like kind of like a see-through, or kind of how opaque it's going to be, right? If you're looking at a hard object, it's going to be very high density. If you're looking at maybe hair or something that's a little bit more vaporous, it's going to be very low density. And then albedo, which is a kind of a, let me see if I can find a good picture for you guys, but expression of the abilities of surfaces to reflect sunlight. So I'm sure there'll be why is everything about this, I don't know what this means. Albedo, let's do Blender. Low albedo, high albedo. So yeah, something, you could kind of think of it like this, right? There's an albedo property, and the monkey in the back versus the monkey in the front, you're going to have different albedos, right? The amount of sunlight that the monkey in the back here is reflecting versus the monkey in the front. So these MLPs that you're using in these Nerfs, right, they don't need to just predict the color. They can really predict anything, right? And that's kind of the coolest part about neural networks like this. You can completely change what the input and the output are. You can add things. So the same way that you could condition this on something other than just text, and condition it on a class or some combination of class and text, or even new things that we haven't even thought about conditioning them with, you could have the Nerf output way more than just the color. You can have it output density, albedo, metallicness, roughness, and maybe at some point in the future you could even imagine outputting physics properties, right? Like elasticity, and I don't know, like the roughness, the hardness, something that's metal would have more hardness. So you can see how Nerfs could eventually be used for everything, right? It's a universal way of encoding information for an object, rather than what we do now, where we have these textures, and then we have these meshes, and then we have kind of maybe some meta information in some file that has the weight of the object and the elasticity of the object, and I think all of that will eventually go away, and it's all just stored inside this neural network that encodes everything there is to know about this object. Okay, MIP Nerf is computationally expensive, based on a large global coordinate based. Yeah, so they're kind of shitting on the fact that Dream Fusion uses a relatively simple kind of Nerf formulation. At NVIDIA Research, they have much fancier ways of formulating Nerfs and storing them in such a way that it's a lot more memory and compute efficient, and that's kind of what they're going to talk about here. Shading. Yeah, right. You have to evaluate the Nerf at every single point, every single ray. So every single ray that you project out, you're going to have to evaluate that multi-layer perceptron at every point along that ray. And if you have a huge amount of rays, let's say you want to look or create an image from a certain camera view, and for each pixel, you're projecting rays out, right? So the more pixels you have, the more you're going to have to evaluate this neural net. And here we go. They're plugging in their thing here, the hash grid encoding from instant NGP, which is what we were talking about. I think we actually have a video for that paper as well. I'm not 100% certain though. I might have read that before this channel even existed. Okay, so we use the hash grid with 2 single layer neural networks which predict albedo and density. So they are also using the convention here of albedo and density. I think they probably could have predicted other stuff too. That would have been cool. Oh, and then they have another one predicting normals. Okay. There you go. So normal, right, is the vector that sticks out from a surface. So it basically tells you which way the surface is oriented, right? When you see these 3D pictures, sometimes they'll have, I think they were here. Yeah, so this coloring here that you sometimes see in 3D models, it's like this like purple, blue, green kind of coloring. That's actually the normal. So green, right, means a normal vector is defined by 3 numbers, right? And it's basically the orientation of a vector in 3D space. So a vector that's pointing straight up is going to be green, right? And a vector that's pointing straight down might be red, I think, in this structure. So this, you can see that the back of the frog is all green because it all points straight up, and then this kind of allows you to see the topography of the actual 3D object. So that's what a normal vector is, and it helps rendering, helps with rendering these things. We additionally maintain a spatial data structure that encodes the scene occupancy and utilizes empty space skipping. So, yeah, and density-based voxel pruning. So, these Nerfs, right, the Nerf is a neural net that encodes an object inside a volume of space, right? There's some 3D volume of space with an object in it. But the Nerf itself doesn't know which parts of the space actually have an object and which parts of the space don't have an object. So when you're rendering with a Nerf, right, you're taking all these rays that come out of the camera. Sorry, let me put I need to stop gesturing without gesturing in front of this camera. So those rays that come out, a lot of times they're gonna go and they're not gonna actually ever touch the object, and then you're gonna spend a bunch of time evaluating the multi-layer perceptron of that Nerf at every single point along that ray when there isn't even anything in there, right? So when you think of this image of this strawberry here, for example, right? a lot of the pixels of this image are actually blank, and you can actually save a lot of computation and memory by not rendering those and not basically performing inference on your NLP or on your MLP just to be told that there's nothing there. So in Instant NGP, this other paper from NVIDIA, they come up with a way of basically taking that 3D space that exists or that the Nerf kind of defines and then voxelizing it, right, which basically just means turning it into smaller little areas of space and then pruning away the parts that don't have anything in it, right, using an octree. Ooh. Fuck. So octrees are a way of breaking up a 3D space into increasingly smaller and smaller resolution voxels, which you could think of little squares. Let's get a good picture of an octree. Yeah. So you have a 3D space, right? This cube, and you break it up into 8 smaller squares, and then you can break up each of those into 8 and 8 smaller squares, and you can actually store this in a data structure that's very, very useful in programming called a tree, right? And there's a lot of algorithms that people have built up over the decades of how to efficiently sort a tree or find values in a tree or prune a tree so that it only has values that are non-zero. And what that allows you to do is have varying resolution. So this rabbit here, I think, makes the best case of it, right? Parts of this rabbit, the voxel is very small, right? You can see it's very small little square that defines the object there. But the parts that are empty are a very large square, right? So imagine how much more memory you would have to use if this entire space was filled with those tiny little squares. It would be a lot more stuff, right? Versus this octree representation, you can have very, very big squares where there's nothing, and then very, very small squares where you actually have the surface of the object and a lot of interesting points. So that's where all that memory and compute efficiency is coming from, is basically not having to do inference on empty areas. And then kind of just the also efficiency you get because you now have a tree data structure rather than some random 3D space data structure. Okay. In our fine stage of optimization, we need to be able to accommodate very high resolution rendered images to fine-tune our scene model with high resolution diffusion priors. So the same for these. Struggles with very high resolution images. I like how in this world they can say 512 by 512 is very high resolution. Whereas I feel like if you asked people on the internet, 512 by 512 is tiny. That's like potato quality. But for this type of work, it's very high resolution. To resolve this issue, we use textured 3D meshes as the scene representation for the fine stage of optimization. Rendering textured meshes with differentiable rasterization can be performed efficiently at very high resolution. Huh, okay. This is kind of really interesting. So there's a second part to this where they're going away from volume rendering. So everything that I was kind of describing before is kind of how Nerfs work in general, where you have kind of an MLP that represents a whole object, and then you basically are doing this ray marching where you're calculating all the rays that come out of a specific camera pose and then evaluating the MLP at every single one of those points. And that's the volume rendering here. But here they're saying that that's actually limited, and you're always going to be it's always going to be computationally expensive. So we're going to be doing textured meshes with differentiable rasterization, but textured meshes are a completely different representation. Okay. So it's a two-step process where the Nerf part of it is really just the first part, and they're doing that at a much lower resolution. And then they have this whole second process where they want to actually learn the fine details. We represent the 3D shape using a deformable tetrahedral grid. Okay. VT is the vertices in the grid. Each vertex contains a signed distance field. And okay, that's the actual signed distance field value. And then a deformation delta VI R3. Then we extract a surface mesh from the signed distance function using a differentiable marching tetrahedra algorithm. Okay. So I think we also did some stuff on signed distance fields previously on this channel. I think there's a video where we actually do a little bit of coding around that. But kind of the thing to think about, right, is that Nerfs don't actually have any representation of the actual object itself, or don't have an explicit representation of the actual object, right? A Nerf will just encodes the information of what this object looks like from a specific camera angle. But ultimately what we want out of this entire pipeline is we want a 3D mesh, right? Because even though I think Nerfs will eventually be the way to represent 3D scenes, right? Just holding it in these neural nets. Right now, we need explicit representations in order to put these into games or movies or use these in other kind of projects. You actually need a mesh and a texture, right? So in order to build the mesh, right, you have to start with some kind of base object, right, which is probably just a sphere, right? So they say this is what they're starting with. They're starting with a deformable tetrahedral grid of vertices, right? So you can think of like a sphere with a bunch of little vertices, right? Each vertex is basically in R3, which means it's just XYZ. It's just a position in XYZ, right? And then there's a signed distance field value also associated with that, which is kind of signed distance field just means how far away from the original point it is, right? And signed means that you can be plus, which is further out, or negative, which is inside, right? So you can take this sphere and you can have parts that dent inwards, and then you can have parts that dent outwards. And then you also have a deformation for each vertex, which is also R3, which is basically how much is that deforming, also in parameterized by 3 numbers, because 3D space has 3 numbers, or 3 dimensions. Okay, so this is kind of the two-step process, is they go from, actually I think that we have everything we need for the course defined. Yeah, we're almost there. Let's look at actually figure 2 now. I think we've kind of read enough about their approach that we can look at figure 2 and break it down. So, overview of Magic3D. We generate a high-resolution 3D content from an input text prompt in a course-defined manner. In the first stage, we utilize a low-resolution diffusion prior and optimize neural field representations, color, density, and normal field to obtain the coarse model. Okay. So, they're starting from here, I suppose, the image, right? They have the text prior, or the text is used to condition a diffusion model that just generates 2D images. Those 2D images, right, the diffusion model, right, knows how to denoise a 2D image. So that's how it creates the image. It just removes the noise, and you give it the text embedding, and it'll just remove the noise. And if you give it the text embedding and then an empty image, it'll remove noise that it thinks it's noise, but really it's just basically pulling that object out of the ether. And now you have these 2D images of that, that should represent that text embedding. And here's the loss here, LSDS, the loss that we saw earlier. And that loss allows you to, right, because you have different views of it, you have different camera angles, that allows you to slowly build this Nerf, right? This Nerf that we were talking about, this multi-layer perceptron that basically encodes that entire object within the weights of it. And you can see actually here in the little grid that they put inside this 3D volume of this Nerf, you can actually see the octree. So you can see how the grid up here in the top where there's nothing is high resolution, right? Or they're big voxels, and then as you get closer and closer to the object and you need more and more divisions of 3D space to encode all that or to like kind of store all that information, the octree gets more and more fine resolution. So this is their kind of like variable resolution octree data structure for the Nerf. And then they call this the Coarse model, right? And then now that you have this Coarse model, you get the 3D mesh, the Coarse 3D mesh, right? Extract the texture 3D mesh from the density and color fields of the Coarse model. All right. We then fine-tune it using a high-resolution latent diffusion model. After optimization, our model generates high-quality 3D meshes with detailed textures. So you see how this is actually well done here, but you see how this diffusion model here and this diffusion model here, this one is going directly into image space. So you see how like the resulting image is basically the same size as the diffusion model here. But in this one here, the diffusion model isn't going all the way to image space. It's going to a latent space, right? And that latent space is where they're adding the noise. And then they're going from that latent space to the actual image space using this encoder here. And now the loss SDS, right, which is now this is the first loss, but now you have the second loss here, is going, rather than from the image space, from the latent space. And now this is probably where they have the this part here, the tetrahedral grid, the deformable tetrahedral grid, and that's how they get to this final high-resolution 3D model. It's like the flow of time here is a bit confusing, right? Because diffusion models, like the flow of time, gets flipped when you train versus when you perform inference. You're adding noise, then trying to model that noise, and then you're removing noise or denoising. So, right, when you have this kind of diagram, like normally in these type of papers, the training and inference kind of go through the same step of process. You know what I'm saying? They're going through the same thing, but because these diffusion models are flip when it comes to training versus inference, it's kind of confusing because here you have two different parts that each flip like that, right? Because they're trained. Stuffed gray rabbit holding a pretend carrot. So this is the actual image that, or the actual 3D model that they trained it on, I suppose. No. There's no 3D model. There's all the original data comes from a 2D data set of 2D images and text. Okay, coming back down, why don't we look at figure 3 while we're here? Qualitative comparison with Dream Fusion. We use the same text prompt as in Dream Fusion. Render it from two views with a textureless rendering for each view and remove the background to focus on the actual 3D shape. Our Magic3D generates much higher quality 3D shapes on both geometry and texture. Yeah, so you can see here, this is Diffusion on the right, and then this one here, Magic3D, on the left. And you can see how Diffusion is much simpler models. And again, they're not doing this kind of multi-stage, multi-resolution stuff. They're just generating at 64 by 64. And they kind of end up with these kind of more simple ones. So it's kind of hard to say because the Magic3D is being much more kind of ambitious. It's trying to generate much more complicated topography, right? Like I would say that a small saguaro cactus planted in a pot, I would actually say the Diffusion here is actually better because this one just looks terrible. You just have like all these little cactus fingers sticking up, and it seems more complicated. I would rather have this one, but it is more impressive that it can generate more complicated things. Right, similar here, right? A carved wooden knight chess piece. This is actually what you want, right? This is what actually a carved wooden knight looks like, but this one actually, even though it's more complicated and it's more intricate and it's more detailed, it's actually less what I would want as a human. So it's kind of interesting to think about, where sometimes maybe more resolution, more detail might not actually be what you want. Okay, so they have an occupancy grid. This is the octree, right? The square, this cube that represents where your object is going to be. Every little voxel within that cube has occupancy, which is there something in this or is there not something in this? And an occupancy grid is basically where you're storing that information. With values to 22, encourage shapes to grow in the early stages of optimization. We update the grid every 10 iterations and generate an octree for empty space skipping. We decay the occupancy grid by 0.6 in every update and follow instant NGP with the same update and thresholding parameters. So this is kind of how they prune the 3D space. You don't want to, right there, it's not like you start with the final object and then you prune it all the way down. They're kind of pruning it. They're pruning that 3D volume as the object kind of materializes more and more. Instead of estimating normals from density differences, we use an MLP to predict the normals. So this picture here, these like bad pictures of this bunny here, this actually is a good example of like one of the kind of bad things that can happen with Nerfs, right? Where when you have something fuzzy like hair, right, you might end up having a bunch of points with a low opacity, right, kind of more see-through, low density. And rather than encoding the reality of the rabbit, which is that it has like an actual like skin, and then that skin has like a specific point in 3D space that you could say like there's a boundary there, right? The Nerf is going to instead have like this kind of region around the boundary where you have the different colors of the fur. And maybe that's better, you know, but in kind of video games and movies nowadays, right? If you had a rabbit in your game, that the skin of that rabbit would be a very, very specific set of vertices, right? That are very like hard boundary between outside the rabbit, inside the rabbit, and then there's a texture that maps to that. Similar to Diffusion, we also model the background using an environment which predicts RGB colors as a function of ray directions. The optimization has a tendency to cheat by learning the essence of the object using the background environment map. Okay, so maybe they're saying that when you have these kind of solid color backgrounds like you have here in Diffusion, right? The model just kind of pays attention to when everything is when it goes from being blue to anything else, and then it's using that to actually get the 3D structure of the object rather than looking at the actual object itself. I don't exactly know what they mean by that. But they're saying that they use a tiny MLP for the environment map. Okay, so a small multi-layer perceptron with just 16 neurons at the end to allow the model to focus more on neural field geometry. We convert the coarse density field to an SDF, sign distance function, by subtracting it with a non-zero constant. Okay, so this is how they're going from the output of the coarse step, where you get kind of the Nerf, and they're going into this what they're going to start with in the fine step. Render the extracted surface mesh into high resolution images using a differentiable rasterizer. I need to like see the picture on this again to try to understand this again. Differentiable rasterizer that bridges the raster and vector domains through backprop. Okay, so vector image, right? Vector images are basically infinite resolution because they define kind of the properties of these lines. So you can keep making them very, very small or very, very big. And here they're saying how you go from vector images to raster images. Right, and they define this in some way that is differentiable. Okay, that's pretty cool. It's a whole other can of worms, but apparently they use that differentiable rasterizer. They optimize the SI, which is the sign of the sign displace or of the sign distance field, and then delta VI, which is the displacement for each vector or vertex, via propagation using the high resolution SDS gradient. Okay. When rendering the mesh into an image, we also track the 3D coordinates of each corresponding pixel projection, which would be used to query colors in the corresponding texture field for joint optimization. Okay, so there's a different MLP for the texture. Right, the sign distance function and these vertices are only going to give you the 3D position of the kind of boundary, right? The rabbit skin, right? They're going to give you the kind of the vertex, the deformation of each vertex, and the kind of sign of that. But then when you actually want to make it an image, you not only need to know kind of where that surface is, but you also need to know what the color is at that. And that's why they're going to take the 3D coordinates of that vertex, right? Each pixel. The vertex and the pixels aren't one-to-one mapping, right? But the vertex is the actual skin of the rabbit, and then the pixel is like it's going to be based on where exactly you're looking at it from and how close you're looking at it. But you're going to have a texture field, which is going to tell you the color of that point in 3D space. When rendering the mesh, okay, this is actually the cool stuff that we were reading about in the background, where they zoom in. So not only are they trying to get different angles of this object, seeing it from different views, but they're also zooming into the object in order to kind of hallucinate the finer details. To encourage the smoothness of the surface, we further regularize the angular difference between adjacent faces on the mesh. Yeah, that's a good point. So these meshes, right, which are composed of these triangles, there's kind of topography to it, right? Topography of 3D mesh. So let's do bad topography. Yeah, so for example, this is important when people do faces in 3D, right? There's some, that's kind of a terrible image, but like for example here, right? Each, wow, I just downloaded some random virus on my computer, but each vertex, right, and its relative position to the vertex around it, and the angle that this facet here and this face here and that face here have, right? There's kind of better ones and worse ones, right? You don't, for example, this is bad, right? This is a really good example of really, really bad topography where the relative angles of these faces to each other are terrible, right? Versus something like this, much better topography, right? The angles between these faces are a lot more smooth, and you end up with a lot more smooth of a mesh, right? And what they're doing in this paper here is they're adding a regularization to their loss that looks at the angular difference between adjacent faces on the mesh, and they try to prevent that from kind of being too harsh. I think the negative side effect with that is that you're not going to be able to get really crispy corners. So you can see that, for example, here in this house, maybe the the edge of this house, right, where the house, the wall of the house meets the floor, right? In reality, you might want to have a high crispiness to I should come up with a better word, but the angle between those would be quite extreme, and this regularization loss is going to make it smoother, which is great for kind of organic and biological kind of things, but for more human-made things that have like hard edges and weird contours and shapes, it might not be as good. So the evaluation data set is 397 text prompts. Okay. Coarse stage is trained for 5,000 iterations with 1,024 samples along the ray, subsequently filtered by the sparse ox tree. So each 64 by 64, right, in the coarse step, you have a 64 by 64 image. For each of those pixels, you're projecting a ray into the volume, which the Nerf defines. And along that ray, you're sampling 10,024 times, right? 10,024 little steps along each ray. And they're filtering that with the octree. So if there's part of that ray that just goes through empty space, they're not going to sample along that part. And that's how they're going to be able to drastically reduce the number of samples along each ray. Okay, batch size of 32, total running time of 15 minutes. Okay, 8 iterations per second. Fine stage is trained for 3,000 with a batch size of 32 and a total runtime of 25 minutes. Both runtimes combined at 40 minutes. All runtimes were measured on 8 NVIDIA GA100s. So yeah, I mean, this is still cheating IMO. Like, NVIDIA A100s are still like extremely expensive. Look at that. NVIDIA A100's graphics card, $15,000. So 8 of them in one cluster. So one server rack with 8 NVIDIA A100s. This is still a disgusting amount of compute. So like realistically, it might be a while until we can actually use this on consumer GPUs. But I suspect that before that they'll have a service where you can just pay per model or per 3D model, not neural network model. Okay, so they're saying qualitatively their model does better. They used Amazon Mechanical Turk to get people to say which one they prefer. And they say which one is more realistic. And then people are saying which one they think is more realistic. Okay, 1 second. I'm going to... I'm going to delete this person who's spamming on the chat. Report. I'm going to report him for pornography. Can I just delete this user? Ablation on the fine-tuning stage. Okay. Oh yeah, there's this whole, okay, we kind of forgot about this, but there's this whole part here where they're gonna allow editing. Yeah, and then the style transfer, that was, okay. Cool, we're not even done with this paper. Ablation on the fine-tuning. For each text prompt, we compare coarse and fine models with mesh and Nerf representations. Mesh fine-tuning significantly improved the visual quality of the generated 3D assets. Okay, so these are, it's kind of like an ablation of how much the fine-tuning is adding to it. And you have just the coarse, which is the 64 by 64, the fine-tuned, which is the 512 by 512, and then the fine-tuned actual mesh, right? And interestingly, you can see how the actual thing changes too. It's not just changing the resolution of the actual final 3D asset, it's actually also kind of changing the content too, right? And if you ask the model to zoom in and show you what the high level details look like, once you zoom out, it actually kind of looks different. Given an input image of a particular instance, we fine-tune the diffusion models with Dream Booth and optimize the 3D models with the given prompt. Okay. Can single-stage optimization work with LDM prior? LDM is the latent diffusion model. Rendering 512 is still too memory intensive to fit into modern GPUs. Therefore, we render low resolution images from the scene model and upsample them to 512 as input to the LDM. Figure 4. Where's figure 4? Yeah, so they're basically saying without this, without the extra step where they do that SDF and the tetrahedral grid and the additional regularization losses that they had for example, the faces, right? Even if you increase the resolution, which they did here, 64 to 256, you get higher quality, but you're still getting kind of these terrible artifacts like these two eyes of the bunny versus the full kind of pipeline works better, right? So the 256 resolution single stage model is actually worse than the 64 resolution coarse to fine model. Can we use Nerf for the fine model? Yes. While optimizing a Nerf from scratch does not work well, we can follow the coarse to fine framework but replace the second stage scene model with a Nerf. In the bottom right of figure 4, we show the result of a fine Nerf model initialized with a coarse model on its left and fine-tuned with 256 by 256. Okay. Yeah, so Nerf versus mesh, what they're talking about there is basically this part here. This is the actual kind of mesh representation, right? These deformable tetrahedral grid composed of these vertices with some signed distance value and then deformations on those vertices versus just a pure Nerf, which is just an MLP that outputs albedo, density, and normal. So that's what they're talking about comparing here, the pure Nerf versus the pure Nerf versus the mesh. Okay, controllable different image conditioning techniques, as well as a prompt-based editing approach to provide users more control over the 3D generation output. Prompt-based editing is the future of humanity. I think that David Friedberg from the All In podcast, which is a great podcast if you haven't listened to it, kind of described it best, where the future is going to look like humans talking to the computer about what they want, right? It's this kind of prompt editing where you're going to say, generate me a picture of a dog, and then you're going to say, make it a smaller dog, and then you're going to say, I want the dog to have its mouth open, right? And it's this kind of back and forth between you and the computer as you increasingly add more detail and edit parts of the 3D model or the image that you're generating, right? And right now we're just doing it for images and 3D models, but eventually it'll be for everything, right? And you'll be able to kind of edit, like maybe it'll generate a whole Netflix series for you, and you can talk, give it more prompts, edit the prompt, and then the Netflix series will change. That's quite far out, but fine-tune model learn to tie the subject denoted as V and generate images of the subject when V is included in the text prompt. Yeah, so you see people do this with Stable Diffusion, where they train it on their own face, right? They want to generate themselves. So Stable Diffusion with your face, right? So people give it like a bunch of pictures of themselves, and then you can generate it with that. And what you're doing is you're fine-tuning the original model with pictures of yourself, and you're telling the model, this picture of myself, I'm going to call it V, which is like a token, right? Like a word token. And now I'm going to say, okay, now the model knows what V means, and it means me, my face. So now when I say generate a picture of a person riding a dragon, it's going to know what V is because you just fine-tuned it on that. We collect 11 images of one cat and 4 images of one dog. Fine-tune ediff-i and LDM, binding the text identifier V, right, to the given subject. They call it binding. It's kind of an interesting word. I haven't heard the word bind in that context. Okay, they're using Atom Optimizer with a really small learning rate, right? Because you're just fine-tuning. You don't want to disrupt these weights. This is important. So, right, when you have these large models, they're always trained with learning rate scheduling, right? So at the very beginning, the learning rate will be something bigger, like 10 to the negative 3. And then over time, it'll drop down to something small, like 10 to the negative 5. Or negative 6. So if you take that model and you try to fine-tune it with a high learning rate of 10 to the negative 3, you're effectively just going to undo all of that kind of second part of the training where the learning rate was much smaller. So when you're fine-tuning a big model that's had this kind of extensive learning rate scheduling, you want to make sure that the learning rate you use is actually small so that you don't overwrite what was kind of put into that model in the last part of the training. So that's kind of why you have to use these kind of small learning rates for fine-tuning. So then they also condition the signal. Yeah, so remember how we were saying that you can put anything here. You don't need to just condition it on the embedding of the text. You can actually condition it on the embedding of the image. And in this case, the image is the style that you want to transfer to it. WText and WJoint are the guidance weights. So they do say that the image has a stronger conditioning than the text prompt. So they have these additional weights here that they tune so that you can control how much the text is controlling the actual image versus how much the style image is controlling it. Okay, I mean, this is barely 50-50 or 40-60 when t equals 0.5. So the t, again, is part of the diffusion model training process, and t equals 0 versus t equals capital T, or 1 usually, because you normalize it to 0 to 1. That's going to be, you're going to have a different amount of noise over that. So the t variable time is like kind of a rough proxy for like how much noise there is. Prompt-based editing through fine-tuning. Another way to control the generated through fine-tuning a learned coarse model with a new prompt. We train a coarse model with a base prompt, and then modify the base prompt and fine-tune the coarse model with the latent diffusion model. This stage provides a well-initialized Nerf model for the next step. Directly applying mesh optimization on a new prompt would generate highly detailed textures, but could deform geometry only slightly. Preserve the layer out and overall structure. Okay, figure 8. We show 2 coarse Nerf models trained with the base prompt for bunny and squirrel, and then modify the base prompt. Fine-tune the Nerf model in the high resolution and optimize the mesh. Okay, here we go. Magic3D prompt-based editing. This is the low resolution image coming out of the first stage of the first diffusion model that generates directly in image space. This is the text that it's conditioned on. And this is the modification of the prompt. They're replacing this kind of blue part here with the blue part here. So they're replacing stack of pancakes with plate of spaghetti, and they're replacing baby bunny with stained glass bunny. And here they're showing how the first, at the top here, we replace the underscored text, blah, blah, blah. We further fine-tune such a prompt-based editing. So I think at the top, they do it. What is the difference between the top and the bottom here? I think one of them, they're only 3 stages. Train a coarse model with a base prompt. Okay, so I think they're talking about, they're trying to show you how the texture and the actual 3D model are different. Right, like they respond differently to modifying the prompt, because I think they modify, or they apply the actual prompt editing to the first part here, right? So they're taking the first part that they already had and then applying the edited prompt. So you're still going to go through this high resolution, going from the kind of lower resolution mesh to the higher resolution mesh. Like that is still the same. I don't think that's modified at all. And they're, I guess, talking about how there's some similarity here. I think the fact that it's able to kind of separate, right? Like here, the bunny stays relatively the same, right? And like going from stained glass bunny to metal bunny, the actual underlying bunny mesh is largely the same. But the really impressive thing here is how we can modify the mesh, right? Like the pancake, the spaghetti and the stack of carrots are very, very different meshes, very different format and structure, but you're still maintaining this kind of idea of the something sitting on top of something. Like this is really quite impressive, right? Where it didn't just try to take the stack of pancakes and then paint them orange to make it kind of look more like carrots. It actually, it's a completely different thing, right? It's like it's actually the long carrot shapes and it's a stack of those. So this really is showing to me like a kind of a deep understanding of the 3D world, which is pretty cool. Right. Although you do see kind of the interesting things here. For example, the cat on a rocking horse. You notice how the cat, or the horse itself, also kind of looks like a cat, you know, and then the tail of this cat itself is getting confused with the tail of the horse. So it is kind of interesting how you have that kind of confusion going here, where because it's thinking cat, you know, it kind of makes the horse look like a cat. And I wonder how you would maybe separate that out, or maybe we just need to make these things bigger and then it just solves itself. We propose Magic3D, fast and high quality text-to-3D generation framework. Benefit from efficient scene models and high resolution diffusion priors. Takes about 40 minutes from a text prompt. But again, that's 40 minutes in a $1,000 or $100,000 computer, so I would say that's a little bit disingenuous there. More preferable by people. They propose a set of tools, but they don't actually release them. And nothing says we can democratize 3D synthesis like not releasing this. I really wish they would have had a GitHub. Okay, let's actually look at these implementation details here. Okay, single layers MLPs with 32 hidden units. This is the MLP inside the Nerf, so the RGB, volume, density, color, and normal. Density-based pruning, right? This is where you prune the octree. They're doing it every 10 iterations. Coarse neural field, there's a bounding sphere of radius 2. We empirically found that using a linear form of spatial density bias helps stabilize the optimization. Huh. So density prediction. Density is one of the things that the multi-layer perceptron outputs, right? And density is supposed to kind of represent whether there's something in that point in space or something like hair, which is kind of more see-through-y, less kind of... You can almost think of it like it's modeling the probability of an object existing in that space, so it's almost like a wave function, you know, in a weird hand-wavy way. But they're saying that when you initialize this density prediction, you can add a bias. Okay, so this is kind of cool. So basically, whenever you are inside this volume, right, where you're going to be rendering your object, you kind of want it to be centered, right? Object-centric neural field. So in general, the density within the inside of that, within the middle of that little cube should be higher than the density outside. So they add this bias, which kind of says that there should be more density in the middle than on the outside, and then that kind of forces the object to be in the middle, which is kind of cool. But this bias actually would not work well for example, a glass sphere that like is perfectly within the boundaries of the Nerf, right? Where all the density is actually on a thin layer along the outside of the sphere. Okay, there is a bunch of augmentations to the camera and light sampling, right? Just your standard, anytime you're dealing with images, you can change the lighting and here, actually, well, what are they actually doing? Okay, so there's a point light location and a random camera center location. And they pick a random... Okay, so the position of the light that is used to illuminate the object is randomized. That's my randomization hand gesture. So you get a little bit more different kinds of lighting, and it acts as an augmentation technique. Yeah, different camera distances, different focal lengths, so they're kind of doing a little bit of domain randomization on the focal length and the camera intrinsics as well. Yeah, so here, training from scratch, right, for the coarse model, much larger learning rate. Opacity regularization. So there's an additional regularization that discourages high opacity, which makes the volume more sparse. And this actually is double good for them because they have their whole hash octree structure that makes it more efficient to render depending on how much empty space there is. So by adding a regularization that kind of encourages low sparsity, you're making your you're going with the strength of having this octree that makes it better the more sparsity there is. In addition to the latent diffusion model, we also consider using super resolution diffusion prior. We render X low with a frozen coarse model to optimize the second stage fine model. Where's figure 9? So fine-tuning the Nerf with super resolution prior fails to add high resolution details. Tmax is the maximum timestamp sampled in SDS. Okay, so they have a different so in this model here, this denoiser, right? They tried a different one here where the image at xt, or at the image at time t, right? Where t is kind of a proxy for noise, is conditioned on the text embedding, the time, and then here they're also conditioning it on x sub low, which is a low resolution version of the image. And kind of they're showing you here that it doesn't really capture, that doesn't necessarily add anything, right? It's kind of an ablation study. We also find that applying the image conditioning only below a certain noise level threshold can help control style transfer. Yeah, so I mean, this is a good point, is that when you're thinking about the style of an image, right, the style is really all about the high resolution, high frequency details. So you want to be kind of doing that at the lower noise levels when your image isn't just completely noise, when it actually is pretty much there, and now it just needs to denoise the like fine high resolution details. Image conditioning can be used for object-centric content transfer to 3D or for abstract 3D stylization. Each column uses a different combination of guidance weights. All results are optimized with noise level threshold T equals 1.0. Okay, so these were the weights that we were looking at before, where W text is basically how important the text embedding is for the text conditioning, and then W joint is the image. So how much weight are you giving to the image conditioning? So when W text equals 0 and W joint equals 100, right, as it is here, there's no weight given to the text embedding, so it's not gonna be anything related to a DSLR photo of a scooter. When it's the complete opposite, when you have 100 on the text embedding weight and 0 on the image conditioning weight, then it's only going to be paying attention to the text. So there's this kind of balance that they try to find here. I think they said 40-60 or 50-50 results in the best performance. Dog wearing a backpack. And then again, they're using this 2D diffusion model to generate different views of this image. So dog wearing a backpack from the front, dog wearing a backpack from the side, and dog wearing a backpack from the back. And then this is what they're actually using in the Nerf. So a lot of the Nerf papers that you see require an explicit data set, usually synthetic, where you have an object and then you have the view from the front, back, and like 100 different other camera poses, but the camera poses are exact, right? It's like you know exactly what the camera pose is relative to the object, and that's why you can have these very beautiful Nerfs that people have created, right? If we just type Nerf, nope, not Nerf. Let's just do Nerf. Computer vision. Right. So for example, this Tonka truck, right? Like they have an actual 3D model of this Tonka truck. So in order to train the Nerf of this Tonka truck, they have hundreds of exact camera angles and pictures, right? They have hundreds of pictures of this Tonka truck from a bunch of different angles. You're right here, you know, hundreds of pictures of this drum set, right? From every possible angle, and it's perfect because you actually know it, right? You like synthetically created this data set and this object. But here, back in our 2D diffusion model land, right, that's not the case. You have very rough images, right? You have the front, but it's kind of the front, the side, but it's kind of the side, of the back, but it's kind of the back, and they're not even the same necessary object there, you know? It might be slightly different objects. So it's much more impressive to generate a Nerf from that kind of, these kind of very rough inputs than from something like this where you have very, very exact inputs and camera poses. Okay, we have more prompt-based editing. More results. This is interesting. This model of this lion has like 3 legs. Ooh, this is quite good. Not only is it generating the computer and the laptop, but there's an actual UI on this computer. That is quite crazy. That's not the right prompt.
This is interesting here too. See how in the Dream Fusion they have the kangaroo is actually much better, much more realistic than here, which is like the kangaroo is like some weird like pony looking thing. I think they use different diffusion models though. Yeah, I think Dream Fusion uses image gen, which comes out of Google, which they had access to because they're from Google. But the NVIDIA guys here for Magic3D, they just use stable diffusion, which is a different diffusion model. Which is kind of sad, right? It just kind of goes to show you that if only these big companies would kind of be more giving with their models and post them and allow people to use them, then research groups from other companies would be able to utilize all of the different diffusion models, perform ablation studies with different diffusion models and see how it works. But kind of the industry is starting to operate in these silos where depending on which organization you're in, you have different models accessible to you and you're going to use different models. So in these kind of like multi-stage pipelines where you're using pre-trained models to embed the text or to, in this case, generate 2D images from different views, you're going to use different models and you're going to get different results. So that's a little bit unfortunate, I would say. Cool. So just over 2 hours, but we did it. This was high resolution text to 3D content, or Magic3D, which is a paper out of NVIDIA. And this stuff is moving very, very quick. I'm very curious to see where we are in a couple years, whether there will be websites where you can just go and type in an orc with a two-handed battle axe riding a giant panda, and it will generate that for you. It'll generate a 3D model that you can then go and use in your game. And the next version of that is it'll generate a rigged 3D model, right? So which has all the animation bones in there, maybe even comes with pre-made animation. So the tools for this are going to get crazy, and I think that we're going to benefit as humans because games and movies are going to get a lot better because of this type of research.